And to continue, our capital letter K, that is our stiffness coefficient in the global coordinate system, is equivalent to this equation. So still, we have the presence of cosine and sine theta and our area in the length for every member. So this is per member. So you have to compute. If we're going to make use of the stiffness coefficient in the global coordinate system denoted by capital letter K, so this is being computed per member. And for our member global fixed end forces vector, which is denoted by F sub F, is actually equivalent to this in matrix form, that is equal to this equation. So we have to identify or solve for our axial forces at the beginning and at the end of the and at the end of the member, as well as our shear forces at the beginning and at the end of the member. And we have to identify also our cosine theta and sine theta. Once you have that one, you simply have to substitute to this equation so that you can compute now for F sub F, or our global member global fixed end force vector. So we have to take note that our F sub F is like or similar to our Q sub F, which is it represents the forces that would be developed at the member ends due to external load if both member ends were restrained against translation and rotation. However, our F sub F's are oriented in the global X and Y directions of the structure, whereas our Q sub F was oriented in the local X and Y direction of the member of the structure. Now we move on to structure stiffness relation. So we're going to establish the structure stiffness relation for plane frame. So this is somehow essential and the same as with that for our previous discussion. So now for this one, it is somehow similar to beams, except that the member global, instead of local stiffness relation, must not be used to assemble the structure stiffness matrices and the fixed joint force vectors. So since we have now our value for our global coordinate system, unlike for the beam, we don't have value for our global coordinate system. So we only have our Q. So now we're going to identify our so the equations that we have is P is equal to S times D plus P sub F, or that can be equivalent to P minus P sub F is equal to S times D. And of course, our S is our structure stiffness, wherein we have to assemble that one using our code numbers. And our P sub F now, we're going to identify first the value for our member fixed force vector in the global coordinate system, which has our F sub F, so that we could identify the value for our P sub F. So it is important first to solve for our member fixed end forces, or member fixed force vector, which is our F sub F, that is in the global coordinate system. So to assemble our S, same procedure that we have done. You have to identify the value for our capital letter K, which has our stiffness coefficient in the global coordinate system, that is per member. Once you have solved that one using the formula for our stiffness coefficient in the global coordinate system, which has capital K, you have to identify the code numbers for each member. So that is the number of the restrained coordinates at the beginning and at the end of the member. Then to have our S, same procedure that we have done, identify the number of degrees of freedom. So you have to write that on top and at the side. Then you try to compare. Then you try to identify the number or the element on our member 1, member 2, or member 3. For example, if there are 3 members, that has a code number which corresponds to the column and the row. For example, you have 1 and 1, so you have to identify that one on each of the member until you finished filling up the elements on our matrix form. Then you simplify. You have now the value for our S, or the structure stiffness. And then for our P sub F, So you have to identify first our f sub f. So our f sub f, you have to simply identify that one. And of course, to identify, you have the formula that was illustrated a while ago. So identify that one, that is per member. So once you have identified, you could now identify the p sub f. Our P sub f is the structure fixed joint force vector. So to identify that one, you have to identify the number of degrees of freedom. So whatever is the number of degrees of freedom, that is in the equivalent value for our P sub f. So you simply have to identify the number of degrees of freedom. Then you have to write that at the side. So for example, if you are now on P sub f, so we simply have to write down. So P sub f, for example, so in matrix form, so if there are 3 degrees of freedom, so you're going to write the code number 1, 2, 3. So this represents the 3 degrees of freedom. Then how to fill up this one? So you simply have to identify the from our computed value for our member fixed force vector, our f sub f for every member. So if you're going to have f sub 1 for member 1, there's a corresponding value f sub 2 for member 2, and f sub 3 for member 3. Of course, there is a corresponding code numbers for each. You have identified that one. Similarly, the code number for our joint, that is the number of our restrained coordinates and degrees of freedom per member. So once you have that one, you simply have to identify if there is a code number 1 for member 1, member 2, or member 3. Then you try to write down on this element. Then you have, if there is a code number on member 1, member 2, you have to add that one. Then proceed to 2. Try to observe if there is from member 1, member 2, or member 3. Then if there is also a code number for 3, for member 1, member 2, and member 3, you have to write. Then you have to simplify. Once you simplify that one, you now have the value for your structure fixed force vector. You have to take note that our f sub f, we have a specific formula a while ago for our member fixed end forces. So you make use of that so that you can compute for our member fixed end forces in the global coordinate system for each member, so that we could identify our structure fixed joint force vector P sub f using the value for our member fixed end forces in the global coordinate system, F's denoted by f sub f rather, denoted by f sub f. So this is f sub f1, f sub f2, and f sub f3. So we simply have to make use of that equation. Of course, we have our equivalent joint load, which is denoted by P sub E. So it's still, that is the negative value for our P sub F. So we simply have to multiply the value for P sub F by negative. You simplify, then you have now the value for your equivalent joint loads. So for our problem, determine the structure stiffness matrix, the fixed joint force vector, and the equivalent load for the frame as shown in the figure. So for our frame, we're given with a 2-member plane frame. So we have here a concentrated load that is acting, and a uniform loading that is acting on 1 member. We are given also with our E, A, and I, and we have identified our degrees of freedom as well as restrained coordinates. So if we're going to identify, there are 4 degrees of freedom, and we have here 5 restrained coordinates. And of course, for that, we can now identify for every member, you have to compute for our K value. For our capital letter K, which has our stiffness coefficient in the global coordinate system. So that we can identify the value for our capital K, we need the value for our cosine theta and sine theta. So of course, if we're going to use of the equation, make use of the equation, then substitute the given values, we can have now our cosine theta equal to 0 and our sine theta is equal to 1 for this example. Now for member 2, same procedure. You simply have to identify also for your stiffness coefficient in the global coordinate system. You have to identify also your cosine theta and sine theta. Then we can now assemble our S for the structure stiffness coefficient for the whole member, because we are talking about structure. So we have to identify the number of degrees of freedom. So basically we have 4. So we have 1, 2, 3, 4. Whatever is written on top should be written on the side. So 1, 2, 3, and 4. Now, for this one, so we have now to identify our elements for the elements found on our matrix form. So we have to go back to member 1 and member 2. If of course, in member 1, you have to specify the code number, and as well as on member 2. So we have here identified our code number for member 1. So you have 5, 6, 7, 1, 2, and 3. So whatever is written on top should be written on the side. Same with member 2. You have 1, 2, 3, 8, 9, and 4. Whatever is written on top should be written on the side. Now, this member code is being taken from our from this, as we have identified our degrees of freedom. So those are the code number or the number for our restrained coordinates and degrees of freedom for each of the member. Then once we have that one, we can now identify our S. So we have now identified the number of degrees of freedom. There are 4. So we have 1, 2, 3, 4 to represent 4 columns, and whatever is written on top should be written on the side. So 1, 2, 3, 4 to represent the row. So now you have to compare this one. You have to check from member 1 and member 2 if there are code numbers pertaining to 1 and 1, 1 and 2, 1 and 3, 1 and 4, and so on. So then you simplify. After you simplify that one, you have your S, which has your member stiffness, structure stiffness. For the whole structure. Now, after that, you can now proceed to your structure fixed joint force vector, your piece of F. So to compute for piece of F, you have to compute first for your fixed end forces in the global coordinate system denoted by F's of F. So our F's of F, of course, composed of axial forces. You have the shear force and the moment force at the beginning of the member and at the end of the member. So for member 1, so that is, we have here member 1. So basically, our member 1 is from our truss. So this is our member 1. So vertical direction, horizontal direction is member 2. So basically from that position, if you're going to observe, you have now your identified shear forces, and you have your identified axial forces and moment forces. So therefore, if you're going to have now your shear force, you have now the value WL all over 2, 120 kilonewton, and moment force WL squared all over 12, that is 200 kilonewton. And you have to take note that the member 1 is not subjected to any axial load, so that is 0. So if we're going to write that in matrix form, you have now the value for F sub F1. And for member 2, that is the member 2 is the horizontal member. So identify also for the F sub F. So we can have now, we have now the value for the shear forces, moment forces, and as well as axial force. It's not also subjected to an axial load. So F axial forces at the beginning, at the end of the member is 0. Shear forces at the beginning and at the end is 37.5 kilonewton. Moment forces at the beginning and at the end is 75 kilonewton meter. So therefore, if you're going to write that in matrix form, you have now the value F sub F2. You have now our fixed force vector in the global coordinate system. You have now the value, and you can write now the code number for each. You have now the code number, and as well as for member 1, you have the code number, so that you could assemble now your piece of F. Piece of F, that is our structure force vector, fixed force vector. So to assemble that one, you identify the number of degrees of freedom, so 1, 2, 3, 4. Then you refer to member 1 and member 2 if there is a code number referring to 1, 2, 3, and 4. Then you write the value, then you simplify. You have now your structure fixed joint force vector piece of F. And of course, the equivalent load is the negative value of your structure fixed force vector. You multiply this value by negative, so you have now the value for your equivalent joint loads.